Hi, we want to look at questions that involve equilibrium of forces. We are looking at JAMB question, particularly a problem from 2006. All right, and then we have two questions from on equilibrium from 2006. But you can check the solutions to other problems of other years when you visit my blog. So that's my blog, examsol.blogspot.com. When you go there, you see a lot of stuff that can help you to achieve your desire as per your exam, forthcoming exam. Right? Now let's see what we have, and let's see how to go about it. Now we have a problem that involves calculation. We have a problem that's 2006 question, that's number 12. I don't know the type actually, because it's not specified. But the question is, a mirror of weight 75 Newton is hung by a cord from a hook on the wall. If the cord makes an angle of 30 degrees with the horizontal, the tension in the cord is what? The tension in the cord is what? Now, question like this, we have to take some seconds, few seconds to look at it and check out how the nature is going to be. Like we have a ceiling, and we have a cord suspending a picture. You get it? That's a mirror. Sorry. You know that this is going to be swinging, and as it swings, we have tension in the cord. So the position of the cord with respect to the wall or vertical axis changes. Now the question is, at 30 degrees with the horizontal, what is the tension in the cord? Now that requires a sketch. The sketch is required. Now we're going to have, this is what we have. We have a support here. Then the swing, the cord swings sideways, and at this point, this is the mirror weighing 75 Newton. That's the weight of it. And then is the tension in the cord, and the angle between the cord and the horizontal is 30 degrees. Now, if that is it, we have to know that the cord is also going to make angle 60 degrees with the vertical, since it has made angle 30 degrees with the horizontal. Now we have to, at this point, sketch for the weight. The weight of the body, you know, this is the weight. Actually, it acts vertically downward. So that is the weight. All right. This can be for the weight. This can be for the weight. We just know that the weight of the body always acts vertically downward. So the tension has a component along the vertical. Right? The tension has the component along the vertical axis. So between the cord and the horizontal is 30 degrees, then between the cord and the vertical will be what? 60 degrees. Right? Because the vertical and horizontal are complementary. So this is 30 degrees, this must be 60 degrees. Now we can find the component of the force, of the tension along the vertical. So the component of the tension along the vertical is T cos 60 degrees. Right? When we solve the tension along the vertical, we have T cos 60 degrees. Now, and that must be equal to the weight of the body for the system to be in equilibrium. Otherwise, it will not be able to sustain the body. Now, so that is it. That means tension, therefore, is going to be 75 over cos 60 degrees, which is 75 over what? 0.5, giving us 150 Newton. So that is it. So the vertical component of the tension must be equal to the weight of the body for the system to be in equilibrium. Okay? So that is it. That is the tension in the chord when the chord makes angle 30 degrees with the horizontal. Remember I said when the chord makes angle 30 degrees with the horizontal, it automatically makes angle 60 degrees with the vertical. Alternatively, we can solve as t sine 30 degrees we go to what? T. Alright, this is the component of the force or the tension along the vertical direction. Okay? And that is T equal to 75 because that's the weight of the body of the mirror. So therefore T is going to be 75 over sine 30, which is T 75 over 0.5. Why did I write sine 30 there? Sine 30 is equal to cos 60 degrees. Okay? So we still have our 150 Newton. The last question that we have in that year on equilibrium is a theory question. The question is in number 14. The question is, the component of vector x along the direction of vector y is 0. When the component of vector x along the direction of vector y is 0. When, now we have many options there. Option A said when x is at an angle of 45 degrees to y. When x is at an angle of 45 degrees to y. No, it's not 0. Can be. B, when x and y are in opposite directions to each other. No, that doesn't justify that it will be 0 at that point. C, when x and y are parallel to each other. In fact, when x and y are parallel to each other, the component of the vector at that point, when the parallel is going to be maximum. Okay, then D, when x is perpendicular to y. Yes, when x is perpendicular to y, then the component of vector x along the direction of y is going to be 0. So the correct option is option D, perpendicularity. So when a vector is perpendicular to another vector, then it does not have component along the direction of that vector. You get it? So what does that mean? It means we are taking x-axis now. We have x and we have y. The component of y along x is 0, and the component of x along y is 0 because they are perpendicular to each other. Okay? And then when they are parallel to each other, then we have maximum resultant. Okay? So that is the answer. The correct option there is option D. The component of vector x along the direction of vector y is 0 when x is perpendicular to y. Alright, so we have answered the questions that have to do with equilibrium in the year 2006. Okay, that leads us to another year. We're going to look at year 2007, but not in this tutorial. That will be in another tutorial. Thank you very much. Please, once again, take your time to visit my blog and check out materials that will help you, because I really want you to succeed this time around and make the most of your effort. So therefore, check the blog, download the free books there, and also watch the videos, and make sure you continue to check them out until you have good understanding as per the concept outlined. Okay, if you have any inquiry, you can visit my you can contact me through my email, or just meet me personally. Since you are my students, I wish you all the best.